as we discover the limitless central limit theorem. This is one of the most fundamental theorems in statistics and also the most important one. We will explore the entire curve, the bell curve, and also some weird names, the P's, Z's, and T's. So let's get started, shall we? The humans have always loved curves. Now we're talking something. Just kidding. In this case, we'll be talking about the normal curve. And what does the theory say anyway? It says no matter how the population is distributed, the sample distribution after a certain threshold will always be normally distributed. That is what the central limit theorem tells us. But again, one important question. What's the difference between a population and samples anyway? Well, let's take example of a die. The numbers from 1 through 6 is the population, the total possible outcomes that a die might have. And this is 6, right? Right from 1, 2, 3, 4, 5, and 6. But the samples can be infinitely many. I can keep rolling the dice for as long as I want. And the numbers I get would be between the same range of 1 through 6. And when I plot those outcomes, the distribution of that would always be normal. But with an extra T, wink wink if you understand the jokes related to the bell curve. We must have more than 30 samples. And how do we come about that number? Well, that's random. Trust me, it has come only by trial and error over the years, and we've fixed a number 30, beyond which the number of samples will be enough for us to prove the central limit theorem. And so now, let us take examples, shall we? Let's take bulb for example. We buy a new bulb and we are all excited to set it up. But do we know the exact lifetime of when it would end? Honestly, we kind of do. We expect a light bulb to last for like 4 or 5 months. These can greatly vary, but I think we generally know how long it's going to last. And thanks to Poisson distribution, this is something that goes on the back of our minds. Let's focus on the heading Poisson distribution formula towards the right, the second image. In fact, the third if you also count the bulb. Therein, we see a formula which almost resembles the normal distribution formula. How, you ask? Well, what if lambda equals to x minus mu the whole square over 2 times sigma square? The exponential term is same, and the remaining is just the constant that's with the exponential term. And this also reflects in its graph. Let's look at image 3 or 4 including the bulb. We see a couple of diagrams. These are both Poisson distributions with varied parameters. In the first image, we see it looks like a normal curve that's slightly skewed. I don't know for what reason the left part is clipped off. Oh, we do know actually. It is because the life cannot be negative. The minimum lifespan could be 0. No matter how we count the time. This looks like a high mean and low variance normal curve, and the other one looks like what a normal curve would look like. But let's take distribution 1 for example. This is the population distribution, or the expected distribution, the total sample space. If we collect samples of these bulbs and we observe the lifetime that they lived up to, this would be somewhere around, again following the blue curve, 5 units of time. And whenever we have these 5 units of time, that will form the mean of our sample as well. And around that will there be a normal curve. So now that we have an example, I think it's a lot more intuitive now that no matter how the distribution is, related or not to the normal distribution, the sample will always be a normal distribution, provided we have at least 30 samples. This number might change, but a general practice is to have 30 minimum. And this means that the samples have a certain mean around which there is a bell curve. The tip of the bell curve at the top. This has nothing to do with the population distribution except the mean of this new distribution, which is, according to our theory, a normal distribution, will be centered around the values which were favored by the previous distribution. A very, very obvious question that might be occurring to you is, why is there a threshold? Why do we exactly have 30 as our threshold? That's a weird number to come about. We've discussed that it's pretty random, but why 30? We have a 29 sample distribution. Is that valid? Does that fall into the bracket? Well, let's answer these questions. First things first, we really want to reduce the standard deviation. Reducing standard deviation is like making things a little more clear. It's like adding pixel values to improve resolution. And using that analogy, when we have more samples in our distribution becomes much smoother. It becomes much more well defined. And thanks to the number of samples, we can easily plot after a certain value whether or not it follows the normal distribution. And it also helps us find the z-scores. Now, what are the z-scores, you ask? That's a measure of knowing how far exactly is our sample from the mean. So if the sample is very far, for example, on either of the sides, on either of the tails of the bell curve, if I may, it probably is not a part of that distribution anyway. And if it lies very close to the mean, this is all relative, by the way, then it probably is a part. But we do need a better measure to understand that, and we will take up that. Remember all the weird letters I mentioned? The Z's, the P's, and the T's? We, I think, already know a little about the z-scores in being a measure of how far away an observation is from the mean, provided the inputs are more than 30. An interesting fact, by the way, looking at the formula to the bottom right, is that the formula of z-score is equal to the x minus mu over sigma. Whenever we want to take the z value of a certain distribution itself, we take the mean of the distribution, we subtract the population mean, and we divide it by the standard deviation of the sample. There's also a formula that says the standard deviation of the sample is equal to the population standard deviation divided by the square root of the number of observations. How do we get that? Well, there's also a formula for the variance. So it all starts at variance. The variance of the population is equal to n times the variance of the samples. And now, what is standard deviation? Well, it's just the square root of the variances. So when we take the square root of variances on either sides, we realize that the population standard deviation is actually root of n, where n is the number of observation, times the standard deviation of samples. And we generally know the population standard deviation because we have a thesis, we have a theory in place, and we really want to check what the sample standard distribution is. So that would be equal to the population standard deviation divided by the square root of n. And now it's time to de-discombobulate ourselves with the heavy terms like t, p, and z, which might be very confusing at first. But now that we know our friend z-scores, I don't think P and T would be that difficult to digest. Remember our good old friend the z-scores? Yeah, the ones that told how far an observation is from the mean. The p-values do the exact same job, and just in a slight different way. But you might wonder, why do we need the p-values anyway if we had the z-score? It was easy to calculate. But well, it never really told us how exactly are we supposed to put our thresholds and understand what values to ignore and what values to use against or for the null hypothesis. This is more like a court scenario where you really want to argue and see whether the null hypothesis is true or not. And for that, what we do is we squish in these values of the z-score into a machine, and what comes out is a golden nugget called the p-values. Now, how I like to visualize the p-values is actually a percentile, if I may. So now let's assume we have a class of 50 students averaging 80 marks. So, well, the bell curve will be centered around 80, with it dropping significantly to a plus minus of 20, which would be the standard deviation. Now, if a child secured only 40 marks, he probably would be in the initial tier of that curve. And we are interested in how many values does he have ahead of him. And the answer could be somewhere around 0.8 out of 1. This is also a probability of finding a point after that certain point having more value, since it's towards the right of the curve. So this is the probability. So let's say I have 40 marks. What are the chances that this class contains a student who scored more than that? And the answer, obviously, at the back of the mind is 1, because that's the average. So there definitely has to be at least one student who scored significantly more than that. But other way of looking at it is we are putting a dive into this heap. And what are the chances that we would find any value that's more than the value that we already have? And it's that probability. It's the probability of 0.8, which says that if you randomly pick any number or any observation out of this curve, that value will be towards the right of this value. And that is the p-value. To obtain the p-value, remember we talked about a machine? Well, that machine is going to come. But first, let's look at a few key points of what p-values really are. The p-values are an estimate of percentile, just like I told you. And looking at that percentile, we know how many times or how many values are further away from that mean if we just randomly pick an observation. In other words, that's the probability. And that's what p stands for in p-values. The probability. Simple, right? And this is a way to catch outliers, and we'll see how. To catch outliers, what we do is we set these thresholds, the weird thresholds, right? So we say, well, a 0.05 threshold or a threshold of 5% is a fair enough threshold. So anything that practically lies beyond that 0.05 mark is not a part of this distribution. And why do we say that? Well, one of the reasons is the bell curve is never ending. And if we don't apply thresholds, we can practically go infinitely large on either sides of the axis, and we still would find every point to be a part of the distribution. So for example, the diabetes count, I don't know if that's a real thing, but let's assume that there is a diabetes count. And every human has it centered around 300, for example. So even 9 billion could be a plausible value with a significantly low probability, but it still does exist. And we really don't want those vague, stupid observations to chip in. And so what we do is we practically truncate the bell curve to a 5% margin. So everything that lies beyond that 5% is definitely not a part of this curve. And this is done by a machine that yields this golden nugget itself. And what is that machine? It's the Ttest. So what exactly is the Ttest? This is the third missing part of our 3Ps jigsaw puzzle. We've already dealt with the Z's and the P's, and now it's time to get into the T's. Hey Ttest, we've finally made it here. You're the third piece of the jigsaw puzzle. and we are ready to fit you in. Well, the t-tests are of two types. Let's assume that we want to check how many students have scored more than or less than a certain threshold. For that, we use a one-tailed t-test because we are only interested in one tail. What is beyond this point? Let's check figure B, for example. The t-test would say the blue area is the part that we want to ignore, and we are checking for the values less than a certain value. So, for example, if this value is 40, it's just a random number, we're just interested in the values that could be less than 40. Now, if we randomly put our hand into this box of values and pick out a value, if the probability of finding that value to be less than 40 is less than 0.05 or 5%, we say, well, I don't think this belongs here. I think this is at the extreme end, and it is safe to say that it's not a part of this distribution. Now, of course, this assumption may lead us to a few errors, but it's a safe bet to take because I think this was at the very extreme end, and it's safe to say that, well, this is probably not a part of this distribution. This also gives us a wonderful insight into a separate world that we'll talk a little bit later. The same goes with C, but now instead of being interested in the values less than a threshold, we are interested in values more than a threshold. So let's say, for example, a guy with 98%. That's an amazing score. That's an amazing person to have. We want to look at the probability of putting our hand into this black box again and pulling out a number that's more than 98. Certainly, this will be very low. The probability of a number greater than 98 out of 100 would be very low. And so even if that beats a 5% threshold, we clearly say that this is an exception too. This is an outlier in terms of being an outstanding outlier, of doing wonderfully amazing to not belong to the curve. But there is also a two-tailed t-test. We want to see what the average students do, or what, let's say, 90% of the students do with a threshold of 5% on either sides. But this is very interesting. So for example, if we want to check the values that can be more than the threshold in figure B, the values will be very high. So if the B exactly belongs at the 5% mark, there will be 95% of the students who have done better than student B. And similarly, if we want to see in figure C how many students have done worse than the student who scored 98%, 95% of the students have done worse. So there is an observation point through which we look and we see how the values would be. But now when we have the thresholds on both the sides, or either of the sides, where do we observe it from? Well, the simple answer is the center. The student who is doing exceptionally good at 5%, at the top 5%, will have the exact same p-value as the student who is in the bottom 5%. So the p-values repeat for a two-tailed t-test, and that's not true for a one-tailed t-test. So that's a wonderful information to have. In a two-tailed t-test, we are interested in eliminating the extremities on either sides. And so with this, welcome to the most interesting, perhaps, part of this presentation. And this is something we widely used in statistics for a very long time, and we will keep using this for a very long time, in my opinion as well. And this shows us the true power of t-tests and p-values and all of these statistical concepts. Every time a new claim comes, every time a new invention comes, it says we have significantly improved on a certain aspect. And by this statistics, we actually put values to this significant, right? We actually see how much it has really improved or lessened or increased in depending upon what the claim is. And whenever we do this, we use the t-tests. We check the significance. If you have done better than 95% of the people, you probably do have a claim for yourself. And if your observation lies beyond the either parameters set in a double-sided t-test or the single parameters of a single-sided t-test, you definitely have done something amazing. And so we use these tests in one of the most crucial aspects of finding anything new. And that, my friends, is the power of statistics. How do you do that? Well, this is more of a guilty until proven innocent sort of a thing. There is a null hypothesis. The null hypothesis says that your value is, well, a part of this distribution. It is very close to the mean, and I don't think you've done anything significant. And we really sort of reject the null hypothesis to prove our point. And sometimes we fail to reject the null hypothesis. So this is like being accused, and we reject the claims made by the prosecutor that you've done something wrong. And if you fail to do that, you're guilty anyway. So this is more like a guilty until proven innocent approach. But if our claim is not true, and if it lies in that average sort of range, within that 90% boundary of the initial distribution, we fail to reject the null hypothesis. So there's nothing like, oh yeah, the null hypothesis can not be rejected. It's like, oh, we failed to reject the null hypothesis. Just to get an idea of how statisticians talk. Now that we know how important hypothesis testing is in statistics and in any branch for that matter, for every new thing that comes up. For example, the vaccines and COVID, they need a lot of t-testing too, to see how significantly have they reduced the counts of COVID cases, or for that matter, the COVID carrying cells in the body. So every new thing that comes up undergoes the t-tests, and the p-values are taken for most cases. Sometimes it can be an ANOVA test, it all depends. But these are the building blocks, the absolute fundamentals. And I think this is where statistics begins. These are the binding pillars of statistics, if I may. And congratulations, we've learned all of that. A few applications can be seen on the screen. I would want you to pause the video for a couple of seconds before the video ends and enjoy the applications of statistics in our day-to-day life. Thank you everyone, and have a wonderful, wonderful time.